super cool.
Yeah. Alrighty, welcome back to 454 midterm review. So, your midterm is done, currently printing. It is not terribly bad, so I will be here to answer any questions you have. We can do it office hour style, or we can just go through what you need to know. So, main things you need to know. Yeah, it's this Thursday, 7:30 in PB basement. Oh no, we're in the basement, of course we are. It's divided into 6 parts. So 15 marks, the short answer, there are all true, false. They're relatively straightforward. Again, this is closed book. You don't have any aid sheet or anything like that. The only aid sheet you have is what I just posted on Discord, and it's fairly lame. It is just a list of the GNU, the GNU GCC compiler options. Just shows you a whole bunch of flags. Hopefully to jar your memory a little bit in case you forget names. But other than that, closed book, not too bad. So short answer, true, false, 15 of them. Then 8 marks for compiler optimizations. So we'll go over that quickly. You should be able to name them and explain them, what they do, the basic compiler optimizations that should automatically run. And then we will do program optimization. So remember lecture 5 where we had that combined thing and we kept on optimizing it over and over again. Something similar like that will be on your midterm. Then there is cache hierarchy. I'll go over an example today because that's probably the hardest question, if there is a hardest question on this exam. And then, actually no, probably not that one. And then virtual memory. Virtual memory won't be too bad. Again, we'll cover it here. And then dynamic memory, which will be not so bad at all. So here, let's go over the topics. So the first few lectures, you should just know like the true false thing won't be anything terribly big. Then for compiler optimization, you should be able to know and possibly name the following. So constant folding. So that's just combining constants, doing the operations. Doing the multiply, that's just called constant folding. Common sub-expression elimination, so if there's a common sub-expression between 2 giant expressions, you can pull it out. That's common sub-expression elimination, only do the sub-expression once. Copy propagation, or constant propagation, so if you know a variable is a constant, just propagate it forward. Then copy propagation, so if you have y equals x, then in place of y, you can just use x in any subsequent thing. So that's just copy propagation. I don't actually need the other variable. Then dead code elimination should be self-explanatory. If any code is not reachable, it is dead. The compiler can just go ahead and delete it. Doesn't have to take up any instructions or anything like that. Loop interchange, so that is just changing the orders of the loops. Maybe it does that, well, it should do that so that it utilizes your caches better. Who knows whether or not it does a good job of that. Loop fusion, so taking 2 loops and combining it together into a single loop. Loop invariant code motion, so that's any constant in a loop. You pull it out of the loop so it doesn't recalculate it, up-teen times. And then the final one is inlining. So we take a function call, and we take the body of the function, just replace it with the function call so we don't actually have to do a function call anymore. So, any question about all these compiler optimizations? Good to name them? More or less how they're applied? Yeah?
Is loop unrolling considered any of those loop things? Or that's just...
Loop unrolling, it'd be too annoying. So in the exam, it just says, assume none of them are loop unrolling as a spoiler loop. Otherwise, your hand might just hurt, right? Yeah? Copy propagation is just like if you have x or y equals x, then you can replace any instance of x with y or other way around. So you just get rid of it. All right, any other question about the compiler optimization? Should be fairly straightforward. If I give you a piece of code, you should be able to apply a few of them and name them, right? Perfect, great. All right, program optimizations. Sometimes the compiler won't perform these things because it's conservative with memory, right? if you write to some memory location, maybe it can't optimize that away. Maybe you have to use your brain a little bit, reorder some things. Maybe it won't apply things because they're in different, I don't know, different C files, or it has to make the worst case assumption about a function, but maybe you know a bit better. So you should be able to apply them. This is exactly like lecture 5. So before we got into loop unrolling, should be able to apply those same things. As a large hint, if you follow the first 4 steps of lecture 5 and be able to apply that to a different piece of code, you should be okay. Questions about that? I'm probably giving away too much here, but whatever. Your labs are slightly hard, so your midterm's slightly nice. So, cache hierarchy. So, this is the one where you should be able to determine how many bits are in a tag, index, and offset, basically how the lookups work. You should know if I say something is a size, a set associativity, you should be able to give me the tag, index, and offset bits, how many are in there. You should also be able to find the hit and miss rate. If I give you a cache and give you some simple array accesses, something like that, you should be able to tell me more or less what the hit rate is or miss rate is. Probably miss rate, no, hit rate, hit rate. So, questions about that? Should be fun, right? Yeah. An example, we'll have another, so I'll leave that to the end. I'll show another example quick of this type of question, and then we'll do an example of that. All right, so yeah, here's an example cache question I already had ahead of time. So given a 32-bit machine with a 2 kilobyte 4-way associative cache with a line size of 8 bytes, how many bits are there for the tag, the index, and the offset? So I'll leave you with this for a little bit, and you can try it yourself and see if you can figure it out, and we'll take it up, and I will write out the same question so we can take it up. So I'll leave you with that for what? I'll give you 2 minutes. All right, your 2 minutes is up. What's the answer? Uh-oh. All right, simple one. How many bits do I need for an offset? Ruh-roh. Yeah.
I guess it's 2, but I'm not too sure.
2. Why 2? Oh, I see some 3s. Yeah. 3. Yeah.
I think because the line size is 8 bytes, so that's no, never mind. I think it is 3 bytes. 3
3, 3? 3, 3, 3, yeah, it's 3. So our line size is 8 bytes. If in powers of 2, that's 2 to the 3, so I need 3 bits to determine which of those bytes I need to access. So my offset is 3 bits. All right, what about the number of bits I need for an index? Yeah.
6?
6, nope. 2, nope.
Is it
5, nope. Oh, geez. Yeah. 9, yay. All right, why is it 9? Okay, so maybe we needed this review session more than I thought. So here is all the things we need to know, right? We have a 32-bit machine. We have a 2 kilobyte cache size. That means it is just always write powers of 2. So 2 kilobyte is 2 to the 11, right? Then if we have 4-way set associativity, that means well, that's 2 to the 2. And we have an 8-byte line size, that's 2 to the 3. So we got the number of index bits from log 2 of that. So if we take our whole address, whoops. So if we take our whole address and we divide it up into offset, and we would always divide our address up like this, right? Offset, index, and then tag. So we know that there is 3 bits here. And then this is what our cache looks like, right? There are S number of sets, and then we have some number of entries per set, which should be our associativity, and our total size of the cache here is the number of sets times how many entries per set we have, right? So which of those numbers do I know? Yeah.
But doesn't it get divided by the size of the cache line as well?
So the cache line is accounted for in the offset, right?
Right, but the cache size, does that not account for the cache line size? Like the number of blocks is depending on like the number of lines it stores also gets divided by that line size?
Whoops, yep, okay.
That's why it's 6?
Yes, it is 6, my bad. Yeah, all divided by the line size. Whoops. Okay. Yes. Okay, for the future question, assume that assume that. So assume I said what's to the 14. That is 16. So for the future question, assume that I was a bit smarter. So 16 kilobyte, so we actually have, you know, to the 9 here. So we were right, it should be 6 bits, but I just modified the question so that my future one's in line, because, yeah, I screwed up and I did this right before I came to class, just so you had an example. Because, spoiler alert, your midterm's printing right now, so this is probably super relevant if I made it up this morning, huh? So, if we have a 32-bit address, that means we divide up the rest of the bits are used for tag, right? So 9 plus 3, that's 12, so I have 20 remaining. So any questions about that? Looks cool, right? All right, so something weird that we might not have seen before is if I say, hey, given the previous question, I ask you what's in the cache, right? Your cache looks like this. There's an index, and then there's a tag, and then there's the actual data that's in there. So I could ask you, is some address like 137 in the cache? If so, what's its value? So how would I go about even starting this? Yeah.
Would you convert 0x137 into binary?
Yeah, I could just convert it into binary, figure out which part is which, right? So if I go back, where is it here? So say I had address 137. So in binary, that would just be 0001, 0011, 0111, right? So does that mean I just, this is my offset, this is my tag. So I should look for an entry that's like ends in 0110, 0100. So if I go back here, does that mean I should just, look at look at one of these entries? The answer to that is no, absolutely not, because tablet. Because is that how I should divide up my address? No, because there's an index, right? So the next 9 bits, 1, 2, 3, 4, 5, 6, sorry, 1, 2, 3, 1, 2, 3, 1, 2, 3. So these would all be my index bits, right? And then the rest of them would be my tag, which of course have leading zeros, and that's just 0. So in this case, my index would be whatever that number is supposed to be. And if I look here, I don't have index whatever that's supposed to be in this table, so you just don't know. So that is my word of caution there. If you get something like that, make sure you divide it up properly and you actually follow your tag, index, and offset. So if we look at, I don't know, what the next address is something like 27007. So if we have an address like that, we can convert it to binary. So 2 is just 00107, 0111. 0 is just 4 zeros, another 4 zeros, and then 0111. So same thing like before. The 3 bits here, they are my offset, so that's offset 7. The next 9 bits, so that is 3, 3, 3. This is my index, right? So my index would be 0, and then the remaining, which would be zeros all up here, would be my tag. So in that circumstance, if I look at it, I would be looking at index 0, which is here, and then looking for the tag that matches that. Spoiler alert, it is the first one. It's there. Yay, it's in cache. Wow. So the offset is 7, so we're looking at the 7th byte. That should be the value 07. Yay. Yeah.
How do we know whether it's the most significant or least significant?
We would tell you. For most significant, least significant, we'd tell you, or I just jammed them all in here just because I ran out of space. So I just jammed them all in here. nothing terribly special about them. Yeah.
So why do a bunch of the entries in index 0 have the same tag?
Why do they have the same tag? Good question. They shouldn't. Because again, I made it up this morning. So yeah, they should all have different tags in order to be valid. Yeah, that would be bonus points if we actually wrote that and you said that. So bonus points. But the mechanics of doing that, everyone okay with the mechanics of doing that? Yeah. The tags have to be different because the tag actually like uniquely identifies a block of memory, right? So if they have the same tag, that means it's the same block of memory. So the same address can't have two values at once. There's no, we're not quantum, that's no like weird superposition thing just yet.
Put a little X and say it's like not allocated, right?
Yeah, we could have ones that are invalid or something like that if we had different tags or something. So maybe there are the same tag, but some are invalid. We won't go into that. Yeah.
So just to confirm, like the 20 bits of tag is for the tag block, obviously.
Yeah.
The index is 9 bits, right?
The index, no, the index itself was 3 bits.
It's 9 bits.
Oh, the index, sorry, 9 bits, yeah.
But don't we only have like 2
I think-
indexes? So like what's the 9 bits used for?
So the 9 bits are used for here, picking out what index or what set they are in the cache.
This is just like a snapshot of the
Okay.
Yeah, yeah.
The offset would tell like which data block.
Yeah, which byte
Okay.
in the data block to actually access, since it's memory. All right, cool about that. That's probably your, I guess I shouldn't super spoil your midterm, but. So, other than that, virtual memory. Main focus of that was like TLB, why it speeds up memory accesses. We don't have to go through all the different levels of page tables. You should be able to vaguely explain why that's slow. It's basically that whole TLB just is another cache for translating a VPN to a PPN. So given a virtual address, you should know, similar to dividing up the cache line, you should know which part of it is the VPN, which part of it is the offset. And the TLB is just another cache, but the data stored, it's not just blocks of data, it's a page table entry, which will give you a frame number of PPN plus like a valid bit or something like that. So, same idea, same cache, pretty much all your cache things line up. We might make it tricky and make the cache TLB, but TLB is just like any other cache, has associativity, all of that fun stuff. So, the next thing, yeah, dynamic memory. We didn't, only important things to know the struct layout and alignment rules. So if I give you a struct with a bunch of data, you should be able to tell me exactly how it's laid out in memory. You don't have to draw byte for byte. You'll probably be given a handy little boxes you can fill in. Wow, so you get some boxes you can fill in, and then you might be asked, I don't know, make it better. What's a better way to organize things in the struct such that everything fits? And then for dynamic memory allocation, you should be able to generally have a high-level understanding of implicit list, explicit list, segregated list, and what the kind of benefits of each of them are. Quick, anyone know off the top of your head what's the allocation strategy for implicit lists? How slow is it? What's it got to do? Yeah.
Linear in terms of both allocated and free blocks, right?
Yeah, when we allocate linear in terms of allocated and free blocks, so it has to jump over both. For freeing, right, freeing's quite fast. For explicit list, for allocation, what was our improvement? We made it linear in terms of free blocks. And then for segregated list, for allocation, we tried to more or less make it constant, right? More or less constant, kind of. It could worst case, it gets a little linear, but not in terms of number allocated and free blocks. So we had those 3 different ones. You should be able to name them all. And then, yeah, some other question for, we can just make it up. So if I have a cache, I don't know, some type of cache, and my block size is, I don't know, weird block size. If it's 16 bytes, and then I have, I don't know, like a big int array, and then I have 4 int I equals 0 to I is less than, I don't know, 144, who knows? Or let's just assume whatever. So it does something and then assigns it to array at index I. So going through this whole array, what would my miss rate be? Yeah.
Miss rate would be 1/4.
Yeah, pretty much 1/4 in this case, right? So if I access A0, well, that's going to be a miss, nothing I can do about it. And then I can figure out, assuming that my array starts cache aligned and everything like that, which we would tell you, then if I miss on A0, it's going to bring in 16 contiguous bytes. That's going to hold 4 elements of this array because ints are 4 bytes. So that will be a miss. It will bring in A1, A2, A3, and then they'll go ahead and hit, and this will just go ahead and repeat over and over and over again. So we'll get a miss rate of, what, 25%. So other than that, we might tell you, maybe the cache size is too small where some of these get kicked out. It'll probably tell you the cache policy used, like last in or least recently used or something like that. So the only thing that can make this harder is like some things might get kicked out by the time, right? So if I said, well, in this case, it doesn't matter because I'm iterating the array once, it doesn't matter. But if I did columns or I loop back on it or something like that, or I just had 2 instances of the loop, then you could imagine something different happening. So questions about that should be not too bad. And then other than that, so, oh yeah, oops.
If it's 145, does the miss rate change to be slightly lower?
Yeah, if it was 145, then the miss rate would be slightly higher, right? Because the last element would be it. That'd just be, is 16 by 16 144? No. Close. 256. Oh, right. 256. Yeah, so if you did 256, or what if I did 257? Well, then I would essentially have 16 misses, or 16 misses for the first 256, then whatever's, then 255 minus 16 hits, and then plus 1 miss, right, for element 256.
Yeah, a little bit more than that, right? Because the inside
is on the 256, and then 1 miss extra.
64. Oh, 64.
So 64 and then plus 1, 65 and 57.
Yeah, 16 should be 64, my bad. Like that. So one more, sorry, number dyslexia power of 2. Shouldn't make up things. Well, I tried. All right, so other than that, yeah, any other questions, let me know. I will also be at my office. I stay during midterms, I just stay overnight in Toronto, so I will be at my office the whole time. If you have any last minute questions, I will be there in and out, so you can come ask me. There's tables outside my office if you want to study there. So you have no excuse not to ask me stuff. There's desks outside my office. Feel free to use them. I'll be around for last minute questions because, of course, other than this, most of you won't study until probably Thursday. Yeah.
I had a question about like tiling. So in your matrix multiplication lecture,
Uh-huh.
you had like some number about the minimum size of the cache for all of the tiles to be stored in. And you had like a 1/3 t to the power of 3.
I corrected it as 3 times t to the power 2.
Okay, thank God.
Yeah. Yeah, it should be corrected. Double check my lecture notes.
Okay.
But I should have corrected that because that was bad. Yeah. All right. Any other last minute questions or anything like that? Again, most of my office hours get just shoved right there because that's probably when you're going to show up anyways. So, anything else for today before we can, you have what, like 3 more days of studying? This midterm, again, should not be terribly bad. If you can do everything we just did with slightly harder with different cache sizes, different things, you can do lecture 5, you'll be fine. All right. Other than that, I will hang out here then for the rest of it. I will let you can use this other time.